Hey, welcome back to Math with Patrick. Today is January 27th, and we're solving the 27th problem from this Daily Epsilon calendar. All right, let's try it out. Find the sum of the digits of any three-digit number times 999. So that's kind of interesting that we can take any three-digit number, multiply it by 999, and supposedly add up those digits and get 27. Now, I'm not really sure what three-digit number to pick, and I do want it to be mostly random, so hey Siri, tell me a random three-digit number. Okay, 809. Let's try that one out. 9 times 9 is just 81, so I'll carry the 8. Another 81, but plus an 8 this time gives me 89. And then another 81 plus 8 gives me another 89. This 0, when I'm multiplying it, won't do anything, so I'll put two placeholder zeros for my 8. 8 times 9 is 72. I'll carry the 7. And then 72 plus 7 is 79, carry the other 7, and then I make another 79. Okay, adding this up, I get 1, 9, 11, carry the 1, 8, carry that one, 18, carry that one, that makes it 10. Okay, so 809 times 999 is 808,191. And if I add up these digits, 8 plus 0 plus 8 plus 1 plus 9 plus 1, let's see. Well, the 8s and the 1s both make 9s together. And then so I have 9 plus 9 plus 9. And that is 27. So I've basically just proven today's problem. I picked any three-digit number. I just chose a random one. Well, Siri chose it for me. And then I multiplied it by 999, added the digits, got 27. But why does this work? So let's just say we have some random three-digit number, and let's call it x. X is going to have three digits in it. It's going to have a 100s place, a 10s place, and a 1s place. And let's call it, how about D2, D1, and D0. D for a digit, and then this 2 would represent how 10 squared would be my hundreds place, 10 to the 1 would be my tens place, and then 10 to the 0 would be my ones place. So I know that x is going to be equal to, 100 times D2 plus 10 times D1 plus D0. And this is just kind of by definition of base 10 counting. With the number 809, it means that I have 8 hundreds and no tens and 9 ones. So this expanded form is the same thing as, well, the three-digit number that it represents. And let's see. I need to multiply this by 999. So I'll say 999x. And here's my idea. We're working with place value. And so tens, 100s, 1000s are really important numbers to use for place value. So why not call this 1000 minus 1 times x? Here I'm producing a 1000, and I feel like this is going to help me out with my place value math. So I guess I have to distribute this. This 1000 and this minus 1 distribute to each of these three terms of my x. So I'll have, well, I guess I'll just write it all out. I'll have 1000 minus 1 times the first term, which is 100 D2. I'll have 1000 minus 1 times the second term, which is 10 D1. And then finally, I will have 1000 minus 1 times D0. So this was me distributing 999 to all three terms of my number x. And it looks like I have to distribute even more. I have, this is going to be 5 zeros at the end of this number. 1, 2, 3, 4, 5. I was doing 1000 times 100, D2. And I'm going to hold off on these minus ones for just a sec. Looks like I'll get a number with 4 zeros, 1, 2, 3, 4, the D1, and then finally 3 zeros, or just 1000. 1, 2, 3, D0. And then I still have to deal with the distribution of that -1. So I'm going to get minus 100 d2 minus 10 d1, and then finally a minus d0. So it's kind of like I have an expanded form of my number, because it's like I have these powers of 10 attached to all my digits. And I could think about it as, well, this right here just tells me that my 100,000th digit is just D2. Then my 10,000th digit is just D1. And then finally my 1000th digit is D0. But here it gets a little bit dicey, because now it's like I'm saying that my 100th digit or hundreds digit is negative D2, and then my tens digit is negative D1, and then my ones digit is negative D0. And I don't know about you, but I haven't seen a number that looks like, I don't know, 354,000 -2, -1, -7. Like, I need digits from 0 to 7 to be able to write this number. But let's see, I think I can compensate. So the idea behind this -2 is that I'm subtracting 200 from 354,000. And so instead of having the digit -2, why not just subtract 200? That would be the same as 3,800 here. So this 2 turned into an 8. And I think I could express that here by saying 10 minus D2 will be that digit. And I borrowed from this one. So that's why I want to say D0 minus 1. So I have borrowed a 1, and I've compensated. I've made it so that I don't have these weird negative digits, and I have figured that part out. And now I could write these digits the way they're supposed to be, from 0 through 9. But then I need to do the same thing and fix this -1 digit and this -7. I guess I could do the same thing. I'm just borrowing. If I minus a 10 off of this, 800 turns into 790. And so the same thing happens here. This digit turns into 10 minus D1, and that works. And I just need to subtract a 1 off of this guy because of some borrowing. Okay, I kind of see the pattern here. I'll do 10 minus D0 for this digit, and I'll take off a 1 because of borrowing. And now I have all positive digits, and it still represents the same value that I had before. All right, so I just color coded it to make it make a little more sense. Here I'm borrowing a digit from the thousandths place and turning it into 10 hundreds. And then I'm borrowing 100 and I'm turning it into 10 tens. And this is just to make sure that all of my digits are somewhere between 0 through 9. So now if I do 999 times x, I will get a number with this format. And let's just look at the previous example just to make sure it makes sense. Looks like my first 2 digits of my 6-digit number are going to be the same 2 as my starting number. Cool. So these 2 line up. Let's see, what else should line up? The next digit is going to be 1 less than the ones place. So this 8 is 1 less than that 9. Cool. And then this hundreds digit needs to be 10 minus D2 minus 1. So I'm doing 10 minus 8 minus 1 is 10 minus 9, which gets me 1. Great. This is going to be 10 minus D1 minus 1. So this digit is 10 minus 0 minus 1. That checks out. And then finally, this last digit is going to be 10 minus D0. So here is 10 minus 9. Okay. So just from this example from up above, I can confirm that what I did here with the digits makes sense because it does line up nicely with the example that I have from before. Well, now let's just sum the digits. We have D2 plus D1 plus D0 minus 1. Then we have, well, okay, hold on. We have 3 minus 1s and 3 plus 10s. So let me actually do a little bit of organization here. So I want to say minus D2, minus D1, minus D0. And then we have 3 plus 10s. So plus 10, plus 10, plus 10, and then 3 minus 1s. Minus 1, minus 1, minus 1. And this part with all these positive digits is going to cancel out perfectly with all these negative digits. So these two make a canceling pair, as do the D1s and the D0s. So when I sum the digits, it doesn't actually matter what 3-digit number I started with, as we kind of knew already. But here the math is telling us this, that the digits of the 3-digit number don't matter. They'll cancel out in the end in the sum. And so I only get 30 minus 3 as the sum of my digits. And that is 27 every single time. Cool. Well, this is my proof that we could pick any 3-digit number, and after doing the multiplication and summing the digits, we'll get 27. I mean, maybe you already knew that based on the problem statement and based on the first example, but I wanted to make sure that I could prove it to myself that it would work for any 3-digit number without actually having to try all like 900 of them. That would be a little bit much. So thanks for coming along. We're all done today, and I'll see you in the next video. All right, see you later.